Okay, what I would like to talk about now, again, is the edit distance problem. And the edit distance problem, remember I had two strings. I had a string S, okay, and I had a string T, and one was of length N and one was of length M. And I wanted to find the smallest number of changes to transform S into T. And my claim was that the following recursive algorithm leads to a dynamic programming algorithm. We're going to define, again, how do I do dynamic programming? I start by defining a function in English that if I could solve this problem, if I could implement this function, I would have the answer that I care about. Dij is defined as the smallest number of changes to convert the first I characters of S into the first J characters of T. And my claim is if I know this, then I know how to find the edit distance between all of S and all of T. How, if I have a function that does this, what is the value of the smallest number of changes from all of S to all of T? Any ideas? If I gave you a subroutine that gave you the minimum number of changes for all that, where you specify the arguments I and J, and it'll convert the first I characters of S into the first J characters of T, could I use this to find the edit distance between the two strings?
Would it be the number that's in D at NM?
Bingo. This is not a hard question. D, N, M. If I had this function, then the value of this is the edit distance of the whole string S into the whole string T, correct? Any questions? Like, I don't get that is an important question. Any questions? We're just calling this with the arguments that mean to the end of the first string and the end of the second string. Once we have a function, okay, defined in English, where there is a value of that function that tells me the answer that I want, I now need a recurrence relation to solve that function, to compute that function. And my claim is that Dij is the min of all these possibilities. Something is going to have, if I have a string S that ends at character, at position I, and T ends at position J, something is going to happen at the end of the string. Either I'm going to take a look at the last two characters, last character of each string, decide that they're the same. If so, then I would pay, if they're the same, then I could have a way to convert the strings where I edit the first I minus 1 characters of S into the first J minus 1 characters of S. Okay, I don't pay anything for this final match. Or it could be that the last characters differ. If so, I am going to pay 1 for substituting this character into that. If this ended in an A and this ended into a B, I could substitute the A into a B, okay, and still pay the cost of pay 1 for that plus the cost of editing the prefixes of these strings. An alternative is I might have decided that I want to insert a character into S, okay? Let's call it a B here. If I insert a B at the end of this, now they will end in a match. Then what do I have to do? I pay 1 for that insertion, and I have to now transform the first I characters of S into the J minus 1 characters of T, because now that B has been taken care of by matching what I substituted. The alternative is I might have instead a deletion from this. If instead I chose to delete the A, okay, then what do I have? Maybe there was an A behind it, a B behind it that now will match with what I have here. But regardless, I would pay 1 for deleting that A, and then I'd have to align the first I minus 1 characters of S into the for all J characters of the second string, plus I pay for the deletion. Do people see where this recurrence comes from? Does anybody see that this recurrence is going to give us the correct minimum number of changes, edit distance, to transform S into T? Or are there any questions? Okay, important thing. Not hearing anything. Okay. So here is a program that implements that recursion as a recursive program. And I want you to look at this thing. What am I doing? This is recursive. I have a string compare recursive thing, and I am calling string compare recursive. See how this is recursive? What is my thing going to do? I'm going to worry about the special cases, the basis cases up here. If one of the strings, if I want to now know, I want to transform the first I characters of S into the first J characters of T. If I is 0, so I've got an empty string, S is an empty string, and T is J characters long, what do I pay? Well, I've got to basically delete. The cheapest way to do this is to delete these characters one by one. I should pay J times the cost of a deletion. Indel is the cost of a deletion here. If, on the other hand, S is big and T is empty, the only way that I could do this is to insert, again, get insert into metric. I have to put in the remaining number of things. I have to do I insertions. If I had to do T deletions there, I have to do I insertions here. These are my basis cases. Otherwise, what am I going to do? I'm going to recursively compute the cost of the editing the prefixes together, and then figure out what's the cost of ending on a match. It's the cost of getting up to I minus 1, J minus 1, plus the cost of a substitution, if there's going to be a substitution. Match is going to be a function that's going to tell me, 1, if they're different, the characters are different, and 2, if they're 0, if they're the same. Or I could get up to here and do an insert, or I can get up to here and do a delete. Okay? I then am going to have logic that is simply going to go through these 3 possibilities and figure out which is the cheapest operation, and I will return the cheapest total cost of the 3 possibilities. Basically, all that the rest of the logic is doing is taking the min of these things. Any questions about this recursive function? Note this is not dynamic programming. You see no table. You see a recursion, but you see no table, right? What is the running time of this algorithm? Does anybody have an idea? Well, I can tell you if you implement this and try to run it, you will be able to edit 2 strings of 12 characters together, but not much more than that. Okay, why? Because right now this is exponential. What is it doing? You're trying to figure out what is S of, NM. Well, it's going to compute S of M minus 1 n. It's going to compute S of m, n minus 1, m minus 1. And it's going to compute S of n, m minus 1. And this is going to work recursively. This is going to compute S of n minus 2, n, and S of n minus 1, m minus 1. And it's going to compute S of, I think, what's the other one that's missing? I guess where I delete from both. Okay, m minus 2, n minus 1. Note that when I build this tree, this thing, okay, is here. It's also here. When I compute this whole recursion tree going down at a height of n, I am then going to immediately come back here and compute the whole thing again. This is like a ternary tree, a base 3 tree of height about n. The running time of this thing is something like 3 to the n. Okay, this is an exponential time algorithm. Any questions about that? So what is the solution? Solution is we are going to use dynamic programming. We are going to use a table to store the calls, okay, that we need. Okay, because if you look at it, when we call this thing, the real parameters we need are really only the position in the first string times the position in the second string. There are n choices for the first value and m choices for the second value. So we can store all of them by basically building a table that stores the ij pairs and then looks them up instead of needing, when we need them, instead of starting from scratch. What is the example? Okay, or how do I do this? Let's look at the code and make sure you understand it. First, I am going to build my dynamic table, programming table, is going to be a matrix of length of the first string by length of the second string. For each cell of the matrix, I'm going to store the cost of getting to that cell plus a pointer to the parent cell. Which direction did I come from to fill this thing out? This is going to be a useful thing a little later. What do I then do? Well, I'm going to change the recursive program, okay, in the following way. I am going to get the intermediate values. Instead of from recursive calls, I'm going to look them up in the table. I am going to keep track of the parent of each cell, which is going to be nice to let me reconstruct the thing. And I'm going to, just for style points, create, again, my ultimate destination is going to lie in a particular cell. Okay, I'm going to have my go cell function look up the cell just so I can use this dynamic programming for other things. Okay. What is the, and I do something a little tricky to keep the indices the way I like them. You can read about that and maybe we'll talk about that in a minute. But what is the big picture? Before I even talk about the evaluation order, let's look at the recursive, the dynamic programming version and make sure you understand it. First, my function is now named string compare, and there is no recursive call. If you look at this, I don't see any string compare being called. Instead, what I'm going to be maintaining, this cell over here, mn, is my matrix, okay, of my dynamic programming matrix. The first thing I'm going to do is initialize my matrix. Now let's just think what that means exactly. here, if my first argument, which I'm going to call, if the first argument, which I guess we're going to call I, let's say these are the ones that go from 1 to the length of the first string. This is for sort of S. And this is, let me start from 0. And this is for string T, and it goes from 0 to M. What do I start out knowing? I know some elements of my dynamic programming cost. The cost of editing the empty string into itself is 0. In general, this is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Okay? This is initializing my matrix. Then what am I going to do? I'm now going to go through, I've got my string S from 1 to N, and my string T, which is going from 1 to M. What am I going to do? I'm going to have basically 2 nested loops. And I'm going to say the cost of cell ij is going to be, again, I could end, if I want for a particular cell here, ij, this is cell ij, what am I going to need to know? I am going to say that I want it's going to be the cost of getting to the prefix of these cells, which is going to be here, diagonally up above. This is where it would go on a match. Okay, so this was the cell from a match. It could also be an insert, in which case I want to go to I minus 1, j minus 1. That I believe is this cell. Okay, and the other one is I minus 1, j, which is this cell. It should be clear that what I'm going to do is this value in this cell is going to be the min of the 3 possibilities I have. Okay? And the possibilities are to end on a match or a substitution, an insert, or a delete. Then what am I going to do? I'm basically, this is just a fancy way to take the minimum of these things. I am going to basically take the minimum of what these 3 options are. And basically the parent is going to tell me whether I ended on a match, an insert, or a delete. Any questions about that? Okay. How many people sort of see this? Again, I'm right now seeing nothing but frozen cameras, and I'm not hearing from anyone. Any questions about this recursive, this dynamic programming implementation of edit distance? Any questions? Okay. What is the running time of this algorithm? Let's stop and think about it. Can anyone tell me what the running time of this algorithm is?
Is it O(n) cubed?
Is it O(n) cubed? The answer is no, but where do you come up with O(n) cubed?
Looking at the 3 for loops, and 2 of them are nested within
Okay,
one.
I see what you're saying here. You're saying, I see 3 nested loops. Okay, Bing, let me try to set that up. I'm seeing 3 nested loops. This one, and this one.
Wait, would it be O(n) squared? Because I just realized they're dependent on different strings.
This is dependent upon the length of the first string, which we said was n. This is dependent upon the second string, which we said was m. What is that inner loop dependent on?
Isn't that constant? Only runs
That is
3
constant.
times?
This was a fancy way of, or attempted fancy way to take the minimum of 3 options, right?
Mhm.
So this is constant. So if you're saying I am good at dealing with for loops, you should be able to look at this and say this is an order n times m algorithm, right? Now, the way I think about it, I don't like to look at the loop. Well, I don't like that they look at the loops because I like to analyze it from the recurrence relation because I know how this thing goes. Let's look back here again. What am I seeing? Am I seeing anything? Well, okay. Well, why do I know it's going to be this? I think with dynamic programming, I guess the other way to think about it, which is maybe what I'm trying to tell you, is I think the running time of a dynamic programming algorithm is the number of boxes times the time per box. How many boxes do we have in our matrix here? How many boxes?
N by M?
N by M, exactly right. And how much time does it take to fill each box?
N by M time.
To fill each box?
Oh, sorry, for each box. Technically constant, but you have to go to like 3 other ones. So.
Well, okay, technically, but 3 is a constant. Okay, so let's think about this. Okay, this here is saying this is the work that I'm doing. And the important thing to see is that this is a constant time operation. Because again, this loop's going around the constant number of times. What am I doing? I am looking something up in my table and basically testing if the characters match. I am looking something up in a table and adding 1. Looking something up in a table and adding 1. Copying something, looping 3 times. Doing an if statement. Does everything see that this is a constant amount of work? And it is a constant amount of work and correct so long as the cells that I need are sitting there waiting for me, right? This is kind of the importance of the order of the evaluation, okay? That this will be constant time if these values are sitting here in my array and I don't have to compute them recursively. But that should be pretty obvious that I can do it. That's what setting an evaluation order is. How can I fill in this array such that the elements that I need are already there? You are telling me we initialized this. Okay, that's the initialization thing. What are the cells that we need? If this is cell ij, I need the cell I minus 1 j. I need the cell I minus 1 j minus 1. And I need the cell I j minus 1. So long as I have these cells waiting here, I can compute the next thing. Does everybody see that? Okay, I can now, if I'm over here, do you see how I can compute this thing now? I've got the 3 cells I need. Once I have that, I can compute this value. I've got the 3 cells I need. Once I do that, I can compute this value. Does everybody see that if I walk down the columns of this thing, at any given moment, I have the 3 cells that I need sitting in the table. Okay? So I can compute the next value in constant time by just looking it up. Any questions about that? Now, some of you may say, wait, but I don't like to go down columns of a table. I'm the kind of person that likes to walk along rows. Is it okay for you to fill this thing up along rows? Suppose I fill it up in a row-centric way. When I get to this cell, do I have the 3 cells elements that I need?
Yes.
I claim the answer is yes. Does everybody see that I could alternately evaluate this in a row manner? Does everybody see that? That's sort of like interchanging the order of the loops in my solution. What about if you're telling me I don't like rows or columns? You may be that kind of person. Can I do this in a diagonal way? Is this cell have what it needs to be filled in? I want to hear some yeses or nos. Does this cell have what it
Yes.
needs to be filled in? Can I now cruise along the diagonal? Do these guys have what they need to fill in? They needed the one above, to the left, and up. Could I have filled these in along a diagonal at a time? Would that have been perfectly fine?
Yes.
Would it? Do people see this? I claim I can fill these things up either going from the bottom of the diagonal, okay, up, or even the top of the diagonal going down. Because at every point I need 3 SLs and they're all ready. Does everybody see that? So the key other part of dynamic programming is seeing that I fill in the cells in a way that the recurrence has what it needs. Okay, and that I claim is the case with this implementation. Okay, any questions about this edit distance thing? Okay, it is kind of important that you guys see what how the edit distance thing works. Any questions? So in fact, I encourage you guys to try to do this example showing how we turn thou shalt into you should. Okay, my claim is that I can turn it into thou shalt into you should in 5 different changes. Okay, can anybody see what those changes are? Okay, well, somehow I'm going to have to convert the th into a y. I might do that with a substitution and a deletion. Isn't that right? And I'm going to have to convert a t into a d. And what is the logical way that that should happen? That's probably a substitution. And I probably also want to convert a into a OU. Is that right? And that's going to be a total of 5 changes. How did dynamic programming find that? Well, again, the cost of editing a blank line into thou shalt. This was the initialization condition. Entering you should into a blank. That was this condition. Then what am I doing? I'm taking a look at every cell in this matrix. What is the cost of editing a y into a t? I could do a substitution and pay 1 more than my diagonal element, which was 0. Or I could take this thing and pay 1 more than that. That would be 2, but that's more expensive. Or I could go from here and pay 1 more than that. That's 2, and that's more expensive. I strongly encourage you to fill out what the, to go through this example and fill out and see how this finds the 5, what you call it, the 5 edit changes. Okay. How does it do it? Remember, the ultimate cost is going to be what's this cell, which is the cost of editing the first, all of this into all of that. To get this value, it depended on a previous cell, which was this. It depended on a previous cell, which was this. I tried to make this bold, so hopefully I'll be able to see it. Here it veered this way because I did a deletion from here. To convert my A into a, an OU, I basically had to get rid of the U and then do a substitution. Okay. Does everybody see that to get every cell, there's a path to every cell that was defined by the parents, okay? And reading this path backwards is what gives us the alignment. That we went from a 5 to a 4 diagonally meant we ended on a substitution. That we kept going diagonally without changing meant we had matches. That we went diagonally and it decreased. We had a substitution. We added insertion. We had a substitution, 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 sub. I mean, match, because the counts are not getting any higher. A substitution and then an insert. Does everybody see that reading backwards from this matrix gives us the actual alignment, the sequence of changes that we made? Any questions about that? In order to know which direction is, that's why we kept track of the parent from each cell. Okay? Any questions about this? Okay, I'm hearing nothing but death, nothing but silence. Okay, anything out there? Any questions? Okay, it is important that you, you figure this out. In fact, I will tell you that your homework 5, now that you guys will soon have this thing done, you can start to think about homework 5, which is the last homework for the semester. You will have to implement the edit distance algorithm. Now, again, I give you complete code for it, so you have a start, but it's important to me that you understand this. Okay, some question about why did I shift left again? What does that mean? Does anyone want to ask that question more thoroughly? Any questions? Okay, so how did we go back and figure out that path? Again, the important point was that every cell depended upon one of the 3 previous neighbors. We want to walk to to reconstruct the string backwards. We want to walk to the appropriate neighbor. This was what we did with the parent field. Okay, the parent field told me whether our last step to get here was a match, an insert, or a delete. Okay, and once you believe that, you can then use this reconstruct path thing to recursively work backwards. Okay, if we want to reconstruct the path to edit S to T, okay, at least the first I characters into the first J characters, what can we do? Well, if our parent is none of the above, that means we hit the upper left corner of the matrix. If we ended on a match, then what did we do? We should reconstruct a path up to the diagonal element and then print out that we ended on a match. If we ended on an insert, we will reconstruct the path up to ij minus 1 and then print out that we had an insert. If we end on a delete, we go to I minus 1, j minus 1 recursively, and then print out the delete. Any questions? Okay. Is this a two-dimensional? This is a two-dimensional array in C. So yes, the table that I'm storing is a two-dimensional array. Okay? That's what I am doing here. This is a two-dimensional array of cells. It's a matrix. And that's what I'm using to store it as my dynamic programming table. Any questions? Any questions about that? Okay, let me see if I wanted to do a variance of edit distance. Okay. Let me tell you, I'm going to give you some very special cases of edit distance. There's some other problems that you can solve, okay, that are problems that you can solve as kind of special cases of edit distance, if you see it the right way. Now, one useful problem is called the longest common subsequence problem, which says I given two strings. I want to ask, is there anything, are the characters, the longest thing in common, where the same characters appear in the two strings in the same order? You know, today is election day. Some of you may be wondering, do the Democrats and the Republicans have anything in common? The answer is, of course they do. They both have an E, they both have a C, and they both have an A. Okay, and they appear in the same order. Okay, the longest common subsequence problem asks, find what is the longest string in common between these two strings. Okay, you understand what the problem is? How could we do this using our edit distance machinery? Okay. And someone's saying, oh, this appears a lot in interviews. Well, it appears in interviews because it's important. It's a good problem. Okay. How do we go and find such a thing? In what way does this seem like a edit distance problem? And in what way doesn't it? What operations am I allowed to do to transform a Democrat into Republican if I want to get the longest common subsequence between them? Can I do insertions from the first, can I do insertions into the first string?
You can do substitutions.
Tell me I can do substitutions? Can I do a substitution? Okay. Actually, I don't want to do a substitution. A substitution takes two different characters and resolves them at a cost of 1. If all I want to do is to find the smallest number of the common characters, I claim the number of common characters is going to be the smallest number of insertions and deletions I can do, provided I don't do any substitutions. You see, how am I going to convert Democrat to Republican? Or the other way around. I'm not showing any bias here. What do I have to do? I am going to claim that to do it, I am going to have to delete the D, okay, delete the, but I'm going to have to insert an R so it matches there. Does everybody kind of see that? I did a deletion and an insertion, and I took care of the D to R thing. If I was allowed a substitution, I would have made one change and not two. If I change my matching costs to be that I pay 0 in the event of a character's matching and being the same, But an infinite amount, if I want to do a substitution, I will do no substitutions. And the optimum alignment is going to consist of some matches. The E to the E is going to match. The M is going to get deleted. A P is going to get inserted. Okay. A U is going to get inserted. And O is going to get deleted. Does everybody kind of get that idea? A B is going to get inserted. A D is going to get deleted. Okay. Until basically all I have left is the C. I guess the C is not going to get deleted. The C is going to stay there. That's going to ultimately match with that. The A is going to match with that. Otherwise, I've got insertions and deletions. Any questions about that? Again, I'm not feeling we are connecting terribly well today, but I want you guys to understand how does the edit distance work, and why is it that longest common subsequence is just a special case? Any questions? What about maximum increasing subsequence? Suppose I give you somebody's phone number. Actually, let's just take a look at it. I'm now going to go on the limb, and I'm going to give you my office phone number. Not that I am encouraging you to use it. Okay. What is my office phone number? It's a good question. Okay. Now, suppose, I guess we start with a 1. What is the longest sequence of digits that are increasing as you go from left to right? I claim, say that I have a 1, goes to a 3, goes to a 6, goes to a 9. Does everybody agree that that's 1, 2, 3, 4 digits that are increasing in increasing order? Is there any way I could have done better? Okay. I guess it's possible I could have started with a 1, a 2. I guess I could have done a 1 or a 6 or a 9, or a 1 or a 3 or a 9, but that's not as long. Does everybody see the longest one seems to be 4 digits? How would I find the longest increasing sequence in a a sequence of numbers? Can anybody see how to do this as an edit distance problem, or as a longest common subsequence problem?
Can you come again for the longest subs?
Say that
For
again.
yeah, can you repeat again the previous question? The previous problem?
The previous
It's kind of
problem
confusing.
was, given 2 strings, find the longest common sequence of letters that appear in the same order in both strings. This, I claim, is an edit distance problem. What about if I am giving you one sequence of numbers, digits? Can you give me a longest common, can you tell me how to find the longest increasing sequence of digits? Is there a way that this looks like one of those problems? Yeah?
Very question. Isn't the longest sequence in this case actually 11226?
Okay, if you're telling me if I'm allowed duplicates, which is a perfectly fair question to ask, then 1, 1, what do you want to say? 2?
226. Since it
That
says
looks better. Does everybody agree that if I'm allowed duplicates, that is a better solution? Right? How would I find the longest solution? Okay. The longest increasing solution. Any ideas? One way might be, okay, if you're really slick, I could find the longest common subsequence to my original sequence of numbers. And what happens when I sort the digits? 0, 1, 1, 2, 2. Does everybody see that? What's my next one? I've got 2 3s. And I've got 2 6s. And I've got a 9. What do I know now? I will claim that if you find the longest common subsequence between this and this, okay, I'm going to claim that any common subsequence between this and this has to be increasing, right? Because all the letters here are in order of increasing value. So if I found the longest common subsequence between this and the original sequence, I would find the maximum ordered one. Any questions? Think about this to make sure you understand how dynamic programming works. That's what I'm trying to say. I'm not sure we're connecting very well today, but I need you guys to look at this and try to understand that. Any questions? Going once, twice. Okay. At this point, I'd like to go all the way back and do the problem of the day. And let's see if we can figure out the problem of the day, which is a completely new dynamic programming problem. And I want to see if people can, I want us to try to think through this one a little bit. This, I believe, was your problem. Am I correct? The one that was on this thing. Good.
Yep.
Okay. So it says that we want to try to break a string into pieces using the smallest amount of work, where the work it takes to break a string into pieces is a function of the size of the string. Okay? So suppose I have a string here that is 20 characters long, but I want to break it at positions 10, 8, and 3. Okay? Another way to think about it is this is like a stick of wood. And I want to cut it into pieces that are eventually, these 4 pieces. But I want to do the least amount of manipulation. Let's say the cost of cutting a piece of wood is proportional to the size of the stick. So it will cost me 20 units of effort to lift the string up now to cut it. What would be the different orders which I might be able to cut this string in order to, the stick, in order to get my pieces? I could perhaps cut it from left to right. I could cut it here. How much would this first cut cost me? If I'm cutting a stick of length 20, how much would that cost me?
20.
20. And now, trouble. 20. And now if I cut this here, how much would that cost me?
19.
19?
I mean, I thought like the second cut.
It's the length from here to here, because this was my stick, right?
Yeah.
How much would that cost me? From 20 to 7 to 3, 17. That's right. And how much would this cost me? Once I have done that, how much left is it? 12. Does everybody see that that's a solution that would take, it looks like 49 if I did this right. What if I cut it from right to left? How much would it cost me? What would the first cut cost me? 20. What would the next cut cost me? What would the second cut cost me? Somebody with a voice, 10. What would the next cut cost me? What What would this last cut cost me after I've done that?
8.
8, okay. Does everybody see this is 38? Does everybody see that that's cheaper? What other possibility could I have had? Is there any other way I could have hoped to cut these strings? The stick? What other possible first stick cut could I have made?
You could choose like the middle one, 8.
Could cut over here at the 8. How much would that have cost?
20.
Once I did that, maybe I'll cut this thing here. How much would this have cost? If I cut that one now,
12.
12. And how much would it cost if I now cut this one?
8.
8. This adds up to, if I'm correct, 40. Okay, the winner seems to be that. You see what we want to try to find? The best possible order to sequence those cuts of strings. Does everybody kind of have an idea of what I'm trying to do? Can anyone give me an algorithm to find the cheapest way to cut those strings? Cut up a stick like that.
I think if we start with the middle, the closest one to the middle, and take it as the first one, and divide it and sequentially and recursively do the same thing. We just look for the middle, the one which is closest to the midpoint.
So a reasonable heuristic is to say always cut it in the middle, right? Is that always going to be the best thing to do? Well, what would I do if I had, I'm going to tell you that that's not always the best thing to do. And in fact, if you want a proof, look at this. This is what we got when we cut it always in the middle. And we got a 40. Okay. So I will claim that it's not a bad idea, but it's not always the right thing to do. Okay. If it's the right thing to do, you would need a proof that it was correct. Right?
I mean the middle in terms of length of the string. The closest to the length.
You would cut the middle. That's sort of what it did. Well, you say the middle of where the length of the string was. Okay. Let me tell you that that's not always the right thing to do. Okay. It's a reasonable idea, but you need, to turn your idea into something, you need to give me a proof that it's the right thing to do. You agree? Until I see a proof that it's correct, I don't know that it's correct. Okay?
Yeah. Yeah.
And I would actually argue that that's not necessarily the right thing to do. You know, again, you could have a lot of world where you've got a lot of things very, very close to here. Your goal should be to try to cut off, a piece where there's, you know, a lot of cuts that's very, very small. The quicker you can isolate that and just chop them off very, very cheaply, the better off you are. Okay, how can we find the minimum possible cut? Okay, can anybody get an idea of what we would like to do this by dynamic programming? Let me try to show you how I would do it, because I think it's still a little bit mystery. I need some kind of a notation. I need a function that if I could compute it would give me the answer. I think maybe I'm going to start to have some notation I need here. Let's let the first markers be. Let's say that we agree that there's going to be n cuts here. Let's make the positions of the cuts P0, P1, Pn, Pn plus 1. So I'm going to say that there's n real cuts and there's 2 endpoints. Does everybody kind of see that? The value of the endpoint is 0. Pn plus 1 is the length of the stick, which I guess in our example here was 20. Okay. What am I going to do? I want to let C sub ij equal the cheapest way cost to cut up the string, the stick, maybe I'm calling it a stick now, from Pi to Pj. Does everybody see that this is a function defined in English? What is the cheapest cost to cut up the stick from I to J? I will tell you that if I had, the question now is, if I had this function, I comma J, is there a way I could solve my whole problem by calling this function with the right arguments? What would be the arguments I want to call it with? Does anybody see? If I knew
the
how to,
array itself,
what?
maybe it needs the array itself, the string itself.
I need, well, the array, this is the input.
Yeah.
Is there, what are the arguments to this function, C sub ij, that would tell me the cost of cutting up the whole stick?
It needs the positions to cut with, maybe.
The positions or the indices? I think that
Yeah.
I want, as someone just said, I think I want to know if I knew C of 0 n plus 1. That's the cost of cutting up from here to here. So if I knew how to cut this up for every subrange from I to J, does everybody kind of see that that would work? Okay. Now, can anybody see a recurrence or a whiff of a recurrence? A way that if I knew how to compute for ij that was smaller, I would be able to figure out the cost of a bigger value. I claim that in the optimum solution, I am going to cut somewhere as my first cut. Does everybody agree with that? Somewhere I got to cut it, right? Suppose I cut it at J. What is the cost of the optimal solution if I cut it at, make my first cut at position Pj? What is the cost of that first cut?
20.
20, or it's the length from here to here. Do we agree? The first cut is going to cost me Pn plus 1, or actually take it back. If this it goes from I to J, I claim it's going to cost me Pj minus Pi. Does everybody agree? If I have a stick that goes from I to J, it's going to cost me the length of the stick. That's what I got there. What else do I have to pay if I cut it over here at J? Am I done? All right, let me call it, I cut it at K. That may be the right answer here. I think I need another variable. If I cut it at position K, this is the cost of making that first cut. What is left to be done? Anybody see it?
Plus the IK.
I've got to cut from I to K. What is the cost of cutting, of optimally cutting from I to K? Okay, what is the optimal cost? I claim it's a
The
special
IK.
case of that. Isn't it C of IK? Isn't that right? If I'm starting, have a wing from I to K? what does it cost to cut from K to the end to J? What is the optimal cost of that?
C of kj.
C of kj. And what is the optimal value of K to cut at? Should I have made my first cut here or here or here or here or here? Which was the best one? I claim the best one is the one that minimizes the sum of this thing. So I claim that it's going to be equal to, let me actually, at the risk of big trouble, let me see if I can do this. Okay. The min, as K goes, from I plus 1 to J minus 1 of this. Okay, let's do a little bit of erasing. Let's see if I can do that. Does everybody now see what the recurrence looks like? The cheapest way to edit from I to J is make my first cut at some K that is between I and J. And if I do that to finish, this is what it'll cost to finish the left. This is what it'll cost to finish the right. And this is what it will cost to make that actual cut. And my claim is the best place to cut it is the one that minimizes these sums. The people, how many people sort of see what I'm doing here? Or is this completely, again, from Mars? Any questions or comments about where this is coming from? Aren't I taking the minimum of the summation? Yes, I'm taking the minimum of these things, of the sum of this plus this plus this. I have the choice. I could make my cut here, or here, or here, or here, or here, or here. Which is the best place? The one that minimizes the cost of doing this, plus the cost of the whole thing. Actually, the cost of the whole thing is the same for all possible cuts, right? So this, it doesn't matter which K I use. Okay? Any questions about that? What is the running time of this algorithm? Okay, let's think about that. What is the running time? How do you count the running time of a dynamic programming? Okay, what is below min? This says that my argument K runs from I, okay, from I plus 1 to J minus 1. Meaning, if this is my I initially, and this is my J, I want my possible cuts can be anything in between it, from I plus 1 to J minus 1. That's why the indices are there. Any questions? How do you tell what the running time of a dynamic programming algorithm is? What is the formula I give for the running time of a dynamic programming algorithm? It is the number of boxes times the time per box. What is the number of boxes that I have here? We agree that the time is going to be equal to the number of boxes times the time per box. Right? How many boxes do I have here? Can anyone tell me how many boxes I've got in this recurrence? How big is my table going to be? Seeing n squared question mark. That's almost right. Well, it doesn't have a question mark after it. That's the difference. Okay? Why is it n squared boxes? What are the possible choices for the left point of a region? If I have this function c of ij, what are my number of choices for the I value? What are the possible first choice indices where I might be interested in Cij? What are the possible, what's the biggest possible I could have, and what's the smallest possible I? Someone with a voice. Is there anyone with a voice out there? Even if they don't know the answer, I'd like some evidence. No one.
0 to the last one.
The first one, I can go from what? From 0 to what? What's the biggest value that I could have? If I have a call here with two arguments, what is the biggest value that I could have? The smallest value is 0. We agree. What is the smallest subrange? Does everybody see we might be interested in something like this? I claim the first index could go anywhere from 0 to n minus 1. And the second index can go anywhere from 1 to n. That is going to tell me that if there are n choices for the first thing and n choices for the second thing, there are n squared boxes. Do people see how I did that? It's what are the possible different arguments you can get. Now, what is the time it takes to fill a particular box? Can you look at this recurrence and tell me how much time does it take to fill a box ij? Or in particular, if it goes from 0 to n plus 1, what does it take? What does it take to fill the box 0 to n plus 1, which is the biggest of these boxes? How much time does it take to execute this recurrence if the values are there?
Constant.
Constant? Well, how much time does it take to look up, to look this guy up in a table? How much does that take?
Constant.
Constant. How much does it take to look this guy up in the table?
Constant.
How much time does it take to subtract this from this?
Constant.
And this whole thing took constant time. How many times are we doing that, though? Remember, we're doing this min over all possible k. How many different k's might we try? Note that for any one k, this is going to be constant. How many different k's are we going to be trying? In the biggest value. What?
N.
N. Does everybody agree that if we were going from 0 to n plus 1, we'd be doing so maybe at the n plus 2 different k's, right? But bottom line, there's going to be, it's the min over n things, where each thing took us constant time. The time per box is going to be order n. And in fact, this is an n cubed algorithm. Any questions about that? Okay. I want you to think about it and see, again, this video is available for analysis after you've thought about this a little bit more. But what's the important thing? We defined a function. If you understood what the problem is, and that may be part of it, We defined a function in English that if we could compute it for all I and j, we would be able to get the target of what we wanted. Then we came up with a recurrence of this. Okay? And this is a recurrence that will tell us the last cut has to be made someplace. We're going to make it at the one that minimizes total costs. What is that? Well, the total cost, if we make our first cut at K, is the cost to the left plus the cost to the right plus the cost of the last cut. And we're taking the best one that's possible. Okay? So we know that we've got the minimum cost. Any questions about it? Okay. Any questions? Okay, think about this, and we will talk about it. We'll talk about any of the. I want you to try to look at these things, and we'll talk about it somewhat next time. Okay. Thanks a lot, and I'll talk to you guys next time.